Okay. Hi all, once again. So right now in this presentation, we're going to see in detail the engineering AI solutions that lie within the Sim Center portfolio, simulation portfolio. So just a brief agenda here. We're going to start with a small introduction. Then we're going to check SimCenter Physics AI and some Physics AI use cases. Afterwards, we're going to talk about SimCenter Physics AI Generate. After that, ROM AI. And last but not least, we're going to talk about HIDS AI Simulation Predictor. So here, as we've talked about, you can see where alters portfolio and enhances SimCenter X portfolio, accelerator portfolio. So simulation portfolio gets enhanced in three main areas in simulation and analysis that we've been talking so far about, the AI solutions that we're going to check now, and also the HPC part. So one thing to note here is that based on McKinsey studies, leaders in AI adoption achieve 4 times the results in half the time. So basically this means that with the development of AI and with the times that we live now, adopting AI is no longer optional. And basically, it is a key differentiator within the competition. So let's start with SimCenter Physics AI. So SimCenter Physics AI is a geometric deep learning engine for fast physics predictions. Basically, in a standard process of development of our products, we have an initial design, then we run simulation on top of simulation in order to find the optimal design that meets our performance, meets our targets. What we want to achieve with Physics AI, what is the vision behind Physics AI, is to utilize, deploy this geometric deep learning model, which is 10 times to 100 times faster than the traditional solver. In this way, we are replacing the solver in order to explore our design space. Then, of course, at the end, we need to run a simulation in order to verify our results. And in this way, we can conclude to the final optimal design. And we have saved time, and Physics AI has enabled us to make design decisions faster. So let's see a little bit technical details here about how Physics AI works, how this geometric deep learning works. So you can think of it as a black box where it gets some inputs, it is trained on some inputs, and learns to predict some outputs. So we call these inputs as node features, and basically, as inputs, we can have any characteristic of our nodes. So meaning, since it is a geometric deep learning engine, we can have, of course, the nodal coordinates of our nodes. We can also have some boundary conditions as the thickness of our part, the material of our part, the forces, for example, that act on some nodes, and so on. We feed this data into Physics AI, and then we train it, and Physics AI learns to predict the node labels, which basically can be any result type that exists in our result files, meaning stress contours or displacement contours or deformation for structural cases, also pressure, velocities for CFD cases, and so on. And of course, also with Physics AI, we can predict KPIs and curve values as well. So physics AI has enabled us to unlock historical data that are, for now, are just sitting aside, and we can't utilize them in order to get insights from them. So what we could do for now is to have parameterized data in order to train surrogate models, to utilize surrogate models in order to predict scalar values and curve values. Whereas now, with the help of physics AI, there is no limit for parametric studies. We can simply utilize our unstructured data, past historical data, feed these into physics AI, train our geometric deep learning engine, and now, on top of being able to predict curve values and scalar values, we are able to also predict fields, contour fields. Here you can see the standard process of utilizing physics AI. So the first step is to gather our historical data from past simulations. We split this data into two data sets. The first one is the training data set, and the second one is the testing. So during the training phase, during the training of physics AI, only the training data set will be used, and the testing will be left aside. The training can be done either locally or remotely if the resources aren't enough locally. And of course, on top of using CPUs, we can use GPUs in order to make the training faster. You can see here some different architectures that exist within physics AI and different hyperparameters that we can utilize during the training. And also during the training, we can see how the training is going, basically through the validation, the training and validation loss curves. And in order for the training to be successful, we need these two curves to converge, both of them to converge to 0. Next step is to validate with our test data set, which has been left aside. So we are predicting on unseen scenarios to the physics AI model in order to see if our physics AI model has generalized well. And in the end, once we are satisfied with the results, we are able to deploy our physics AI model in real-time exploration. One question that me and my team has been asked so many times is how do we know that the geometric deep learning models are correct? So basically, we've developed two metrics in order to be sure, have an estimation on how close are our predictions to the simulated results. So the first metric is when running the testing phase. So basically this metric has to do with the prediction error between our physics AI predictions and our solver, our simulated results. So this step helps us to see if our physics AI model has generalized well during the training and has been trained sufficiently. And the second metric has to do when deploying the physics AI model and basically answers the question how similar is the new design compared to our training data set. So you can see here when deploying the physics AI model, on the top right corner, we get a similarity score. Basically, this similarity score tells us how similar is our new unseen geometry and also the characteristics of it, let's say, compared to the training data set. And in this way, we have an estimation on how close are our results compared to what if we had run the traditional solver. So the value for the similarity score is between 0 and 1. Of course, 1 means that the geometry that we're reporting is exactly the same with one of the geometries that had been used for the training. And we are satisfied that our predictions lie closely to our solver if the similarity score is above 0.7. Of course, physics AI is domain neutral, meaning it can be used across all these different domains, industries and domains. So whatever results files basically we've got, we can handle them inside physics AI, we can train on them. And now let's see some physics AI use cases, a couple of physics AI use cases. So the first one is a crash application for Magna. So basically you can see here the crash simulation, which is highly nonlinear simulation between two vehicles. And we want to predict the displacement of the bumper. So in this case, unfortunately, we hadn't had an already created data set, but we created one through DOE study. So we varied the thicknesses in the materials of this bumper. And after creating the data set, we fed this data into physics AI. We trained with them physics AI. And now we are able, during the deployment of this predictive model, we are able to get our results within 10 seconds, whereas the traditional solver takes 14 hours to run. Another AI use case for airbag design for Continental. So basically, Continental have an experimental setup in the laboratories where a pendulum drops and goes to hit a wall, but then the airbag deploys and prevents the pendulum from hitting the wall. So in this case, once again, we've got a complex physics simulation. And in this case, we want to simulate to predict the contact forces on the surface of the airbag. So once again, we're creating the data set through running DOE with the help of Radius, of the explicit solver of Radius. After that, we train physics AI, and when deploying it, we are able to get very accurate results, very accurate contact forces results within 30 seconds, whereas the traditional solver takes 2 hours. One thing also to note here is that apart from physics AI being embedded into SimCenter, Hypermesh, SimCenter, SimLab, and so on, physics AI, SimCenter Physics AI is also embedded in SimCenter StarCCM+. So in this way, we are able to get closer the CFD simulations with the AI models, with physics AI models, into one unified environment. Now, let's talk about SimCenter Physics AI Generate. So as you can see in the slide, it is an experimental software. So keep in mind that we're expecting its official release at the end of 2026. So this, I want to distinguish that Physics AI Generate and Physics AI are two different softwares. Physics AI Generate is a 3D generative AI software, meaning it uses diffusion models in the background. So we can see where Physics AI Generate stands in the whole design process. So we've talked about where physics AI stands, basically to replace the solver, the solving time. Now, physics AI generate is responsible for replacing the manual CAD editing. And in this way, the vision, let's say here, is to having automatically created a new design concept with the help of physics AI generate, feed this into physics AI, and being able to predict very fast the results. And in this way, we're able to reduce even more the time needed in order to do this cycle, design cycle. So let's see the process once again of physics AI generate. So the first step we need to do is to create the data set. So basically, we are using our historical designs that once again just sit there. So we are using our historical designs alongside with our design targets. These design targets can be any custom scalar value. For example, it can be design performance, for example, a max displacement that is observed in our design, or a max stress, or it can be even such as the cost of the design, or the dimensions of the design. We use this data set in order to train physics AI generate. So once again, the training can be done either locally or remotely, and on a GPU as well. And when deploying the physics AI generate model, we simply set our new design targets. Then within 10 seconds, physics AI generates a new design concept for us that basically, essentially, respects the design requirements, the design targets that we have defined. Basically, it respects these design targets. Now let's move on to Siemens AI, which is a reduced order modeling technique for complex systems. We've talked a little bit previously on this, but let's get into more detail now. So Siemens AI is a proprietary method that combines deep learning with dynamic system theory. As we previously talked in the previous presentation, we need to have parameterized data into a CSV file, and basically ROM AI trains on this data. It can be used both on static models and also on dynamic models. And its power, let's say, is when it is deployed for dynamic models, and this is where dynamic system theory comes to be utilized. And the usability here, it's very easy to use, and it can find application in different use cases. For example, it can be used to replace a traditional solver, or it can be used, it can be exported as FMU, and it can be installed on hardware for real-time predictions, since it's very fast, in controller scenarios, for example. And you can see here, Chery Automobile Company has already adopted these solutions, and they are satisfied, totally satisfied with it. Coming back to the AI-driven airbag study, this is the experimental setup that I was previously describing. So the keynote here is that you can see that we have two different tools, Physics AI and ROM AI. And basically, depending on the goal and on what we want to achieve, we can utilize each one. So you can see on the left-hand side here, we want, in this use case, we want to predict the contact forces. So we want to predict a field of values. In this case, we utilized Physics AI. Now, in the ROM AI, on the right-hand side, for example, we want only to predict some curve. For example, here, the acceleration curve of the pendulum. So if we have parameterized data, and we want to predict a curve, we can very easily use ROM AI in order to do so, and there is no need to use Physics AI. So depending on the use case and what we have, and on what we want to achieve, we can utilize the appropriate tool. Now, last but not least, for the HIDS AI simulation predictor, basically is a software, is a tool that helps us to accelerate and boost our optimization studies with AI model. So I'm sure that you already know, but let's talk about a little bit of the challenge of the MDAO process. So we have very long simulation, very long running CA simulations. The compute costs are high. There is always a pressure to reduce time and effort, but in parallel, improve the performance of our product. Also, the trustworthiness part comes when the optimal design is going to be accurately manufacturable, is able to be manufacturable and operate smoothly in the working environment. And also, there is a high desire to reuse existing knowledge during our optimization and our DOE studies. But there are no means of doing so. And this is where HIDS AI simulation predictor comes, which is basically an AI technology that boosts our optimization studies with trustworthy and accuracy-well AI models. But let's see here, how does it do it? How does it do so? So basically, during the optimization study, there is a dynamic decision on whether I'm going to simulate this particular design, or I'm going to get some predictions from my AI model. So this is done basically based on the parameters, on the parametric side. So based on the parameters, based on how far the specific design is on the limits of my design space, or how many design points have I used in order to train the AI model. So this is a highly dynamic decision on whether I'm going to simulate the results or I'm going to get the predictions. And of course, while I'm simulating more and more designs, the accuracy of the AI model improves, and I can rely more on the AI model. You can see here in the video, for this specific CFD use case, when we want to maximize the lift and minimize the drag, that while I'm running the optimization study, you can see here with the blue dots, that blue dots represent the simulated designs, whereas the green dots represent the AI predictions. You can see how the blue dots are more on the Pareto front, where are the limits of my design space. And by the end of the optimization, we have successfully saved 45% of compute time. Again, here, as I previously talked about physics AI, sim-centered physics AI, and ROM AI, when to use HIDS AI simulation predictor, because not all the cases are the same. So when we have time-consuming CA analysis, or when we need upfront that our design space is vast and we've got many parameters and our design space is vast, meaning that we will have many design iterations and our optimization is going to be very long, we can use HIDS AI simulation predictor. And also, when we want to leverage insights, when we want to leverage information, data, that either come from the same optimization study, or this data can be from prior results, prior optimization studies. And that's all by my side for the AI solutions. Thank you once again. And please feel free to ask any question if it comes into your mind. Yes, yes, of course.
AI or HIDS AI if I want to test heavy machinery, but I would like to see the changes of stress on parts when I change the dozer plate angle or something like that. Is it possible to use the ROM AI, or is it better to use HIDS AI?
So the first question is, do you want to run optimization study? So you want
see how I minimize the stress on multiple parts when I test the dozer plate mechanism.
Yeah. In this case, I'd say HIDS AI simulation predictor is better, is the tool to go for, because you will have long-running optimization. And if, in this case, you want to simulate, to find the contours, to see also, to visualize the contours, it's better case for HIDS AI simulation predictor. Whereas for ROM AI, you have to rely on, let's say, some KPI values. For example, the maximum stresses, or so on. Yeah, no problem. Okay, thank you also. Thank you.